Please note that in this video, when I refer to Q, what I'm referring to is Q on the dial. What I actually mean is the dissipation factor, which is 1/10 of the value on the dial. I realize this is quite confusing. The problem is the dial shows Q dq and the function on the side shows C dq. So for the purposes of this, until I start talking about coils and induction, everything I'm talking about is dissipation factor. The reason why I use Q is because it's the Q dial. This is the Q knob, right? But everything is actually having to do with dissipation. We're talking about capacitors, and therefore it is dissipation factor. And everything on the paper, I mentioned Q, and sometimes I call it D, but I just wanted to clear this up before I get into the video. I found this particular condenser to provide a great example. This is a condenser from a points ignition from an old Volkswagen. And this reads, this is a 0.25 microfarad condenser. And it actually reads 0.392 over here. The purpose of this one is to demonstrate a particular function of this machine, because the Q for this condenser happens to be less than 1. And because it's less than 1, and you'll take my word for it, it happens to be dialed in at exactly, on this knob, 0.6, right? So 0.6 shows the highest amount here. Now, one of the functions of this particular impedance bridge is that when it's less than 1, you have the ability to have an extremely high resolution for values under 1, right? So to see if the unit is accurate when going from that conversion to this conversion, because as you know, that when you switch to this knob, the 0 to 10 knob turns into a 0 to 1 knob, right? And we'll demonstrate this. So right now we see that we're sitting here at the in and around, well, you see that we're at the 0.6, right? So I turn the knob right here to the high resolution, right? And now it becomes a 0 to 1 knob. So I'm going to dial this up to 6, which is now going to be the 0.6, as it's a tenth of that. And you see that I went a little bit past there. And you see that that representation does work. It does transcribe very well. So the capacitors that are back there are working very nicely. I mean, you couldn't hope for better considering, you know, how this knob works. That 0.6 perfectly transcribed itself to the 6 on here, moving back and forth on there. So that shows me that anything between those two capacitors is absolutely perfect. The function between the D and the DQ on this is just fine. It also tells me that the functions between the DQ and the Q for this should be fine as well, because it's using the very same capacitors, right? So I've also solved for that as well. That being said, I pretty much have a belief at this point that all the functions on this knob are done. All the functions on this knob are now done. All the functions on this knob are now done. And all we really need to work with now is the location of this knob. And if we could solve, obviously, for ESR, or if we could solve for Q, then we could solve for ESR and determine that this knob is good. And we can do that, and then we can move on to inductance. So that's what we're going to do. They talk about a couple of ways in the book to set this knob to actual 0. And one of the ways is really non-academic, which is to turn the shaft all the way to 0 and pop the knob in the 0 position right here, and it's 0. The other way, a bit more technical, talks about measuring the back of the unit. They have a convoluted way of using this to measure exactly 160 ohms, but you could use an actual multimeter that you would measure the back of the potentiometer for exactly 160 ohms, and then when you had that, you would turn this and align this to 0, right? And that would be actually 0. And what I found was this, and I believe this to be the most accurate of all. I have a capacitor tuned in here. It's an 8 microfarad capacitor. It's reading 7.62, right? And the Q is about 3.4, whatever. When you look at the Q on this stuff, or 3.2, when you look at the Q on this stuff, you can see that there's not an exact measurement between these under 1, right? So it's just how it is. But what I want to point out is that if I dial the Q all the way back and detune this circuit, right, we'll go into the positive, right? And there's 0. And this is how I have it set up. But the important thing to note is that the needle does not move under 0. It becomes irrelevant. It no longer affects the circuit. So the needle is not moving. This is the end of the potentiometer. This is whatever that resistive value is, and I don't recollect exactly what that value is, but this is 0, and you'll notice that needle over here will not. Let's see if I get them both in the frame. That needle will not move until I get to 0. See, it's not moving at all, and just as it hits 0, it'll start moving. See, there it goes. And if I go back, it's moving, and it's no longer moving. Now, all this is just dead play. So the knob's moving, but that is not. So what I found was if I set it just like that, just to the point where it starts to react with the circuit, I get the most accurate measurement. And obviously, if I set this up again for 3.2, it'll tune that, I went past it. Right there, it'll tune that circuit for that capacitor, is what we're going for. So that's how I set up this knob for Q. And obviously, if I start doing some computations with this Q to get the ESR from the dissipation factor, we can see how close I am with those values. The problem is, again, like I said, frequency and capacitance, and obviously pi being a constant, this is always going to be an issue. So we're going to have to work within a tolerance. You're not going to have exact measurement in ohms. We're going to be off. It's nice if it landed right on the 3 or in the halfway, but when you start getting to areas like this, I really don't know what that value is. It's kind of taking a guess. But as far as Q goes, if we look again, we could see that when we hit that 0, I was very careful about this. It's still moving, and then right at that dash, it stops moving, and it's just nothing's happening right there. So this has no effect on the circuit whatsoever, and that's why I've made that 0 start right there. So here we have a capacitor. This one is 8 microfarads, and it's all dialed in already, and we have it reads 7.63 microfarads. It's reading here on the left hand side is I'm calling it 3.2, right, the dissipation factor. And the purpose of this demonstration is to take these values, or Q in this case, is to take these values and with those values plug it into the equation and arrive at an equivalent series resistance. And starting with those values, and I should also point out that I'm using 2 different terminologies, and I realize that because I've been going through a lot of my historical notes to figure out some of the problems I have with the equation, and some of the older things use power factor, and power factor is a percentage thereof. So disregard that. Just know that the number that appears on this, so for the purposes of 3.2 in the equation, becomes 0.32 for the purposes of writing it in this, and that's all you really need to know, right? So I take, knowing the capacitance that was read and the value of Q or D on the dial, on the DQ dial, we end up with 3.2. I divide that by 10 to get 0.32, right? And the ESR is going to be that value, 0.32 divided by 2 times pi times frequency times capacitance. So we're going to end up with 6280. All the measurements done on this unit is 1 kilohertz. And our value obviously is going to be converted into a decimal. So that's going to be .50762 for 762 microfarads. And that gives us ESR of 0.32 over 0.04783536. And little calculator magic ends up with an ESR of 6.68 ohms. So from this machine, without using any modern technology, if I can focus today, we ended up with this value. So let's take this capacitor off of the unit, and we will attempt to hook it up to this machine right here, and we will measure it and see what we get. Let's turn on, I'm using the MESR 100. Let's hook it up. Which side is negative? That's negative right there. And then this side is positive. Not easy one hand, that's for sure. And the MESR 100 says 6.39. So not far off. I mean, for ESR, considering we're working with an analog device, I mean, that is god-awfully close. That is impressive. So I'm very happy about that. That is impressive. I mean, consider the following. This is dead accurate, right? So this is as accurate, if not more accurate, than my my LCR meter, right? So that's to be expected. This, not so much, right? And this is a fundamental part of the equation, right? Because this is you know, this is if this is off by a little bit, pushes that equation, and there's no hash marks between the 3 and the 4. I said 3.2. That just as well could have been 3.1, 3.3. Who knows, right? As far as it working well on the meter, yes, but there's no precision over 1. If it was under 1, I could have got extremely precise values. If they put little tack marks at least all the way through 10, we probably could have got really precise values. This machine was not designed to compute equivalent series resistance, obviously, but the fact that we could get an ESR value that is so amazingly close on a piece of analog equipment with no digital circuitry whatsoever, that by the way, I could get the ESR on this unit, right? But I have to use this other unit to get the capacitance, and then I need a third unit to get the resistance if they're obviously not of a capacitor. This one will get a small amount of resistance if it's low, right? For AC, not DC. But this unit actually does all that without any digital circuitry at all, and does it with a degree of precision that matches or exceeds these two units together. So that's pretty cool. I think we could say that if we can achieve an ESR value that's so amazingly close, I think it's off by 0.4 ohms, right? 6.4 something is what we saw on there. Then this knob would have to be really close to derive that value on DQ. And because this knob is close, and because we've proved that out, I think we can move on to inductance and do that. So that's what we're going to see next is measuring inductance on a coil and dissipation and Q. Inductance is set up very similar to capacitance, except obviously we're going to be setting it for L. When first measuring a coil, we start with the DQ and assume that the Q is not going to be significantly high. If you cannot read the Q at 10, if it's going to be above 10, then you would switch during the measurement to the higher 0 to 1,000 reading. But when you're first making your measurement, LDQ is where you would be at. A notable exception is that when you're setting up everything and you have everything set to 0, the Q dial is actually set to 5. Sort of revealed to me what the detent was for in the knob. I had mentioned that there's a detent in here, that sort of you feel a little notch in there, in and around 5, which I thought was kind of foolish because you're going to be setting this knob up when you calibrate it, and the calibration is not going to necessarily be at 5. So the detent in mine is right there, but I'm not using it because the calibrated position of 5 is right here. So kind of stupid. But anyway, once you do that, very much like the capacitor, we make sure our gen level's all the way down. we set our AC level right here to 0, and then once we're at 0, we turn our direct current, or we turn our generator level up till we balance this. I'll tell you right now, here's an old coil I got from a this is a radio project I worked on a long time ago, a little radio with using a razor blade and a pencil kind of thing. And this measured 0.192 millihenries on the LCR meter. So before I did this, obviously I measured it on the LCR meter. So I'm getting this to 0 right now, and for the purpose of time here, for the sake of time, I got this set at 10. I got this set at 100 microhenries as a measurement, as a multiplier, right? So what I'm going to do, my air conditioner just shut off. We'll just set that again. There we go. I'm going to set this to 1. And I'm going to turn the knob here and see where we hit our threshold. Work with this other one here. Oh, there it is right there. Right there at 99. Let me turn it up so we get, just like on the capacitor, when you dial it in, you turn it up to full throttle there. Gives you better resolution. And I can see it's I'll tune this in, then I'll come back to it. The problem is I had the air conditioner turning on and off, kept adjusting the needle. That's problematic during the summertime here. What I ended up with was a Q of 1 and a value of 199. So 0.199 millihenries is what I got. So, or 199 microhenries. And by the same token, I could turn it up to 1 millihenry and do the same thing. So let's do that now. I've changed nothing on the left hand side. However, now I've changed the multiplier to 1 millihenry. And on the CRL knob, it is now 0 plus 0.19. Giving us obviously less resolution than the other one, but effectively 0.19 millihenries of inductance, which comes very close to 0.192 that I got from the digital meter. On the other resolution, using the 100 microhenries, we did find that this actually read 0.199. Obviously, you really can't see the 0.1999 on this one, but this is how we measure inductance on here. Because this particular coil has a very low Q of 1 and well under 10, we didn't need to use the 0 to 1000 scale that is provided on the inner portion of this knob. But if we needed to go that route, if during tuning we found that we got all the way up to 10 and we still weren't able to tune it in, obviously we could then turn that knob and do that. But for the purposes of reading those values, obviously what would happen is you'd have much less resolution with regard to being able to find precisely what that Q is. Obviously, that is the trade-off. However, this shows how this device can also very precisely read inductance of a coil. As you see here demonstrated, we were able to read with great precision the amount of henries of a particular coil using the IB-2A, using this function as displayed. I'm measuring the inductance of this coil that I have from a very nice crystal set that I got in Switzerland. This coil that I have is wound for 510 kilohertz. I happen to know this. It came with a couple of coils for this set, and this is the resonance of a tank circuit along with the capacitor, variable capacitor supplied with this coil or the radio. So I know in and around where the resonance is. So what I'm using is the 1000 hertz or the kilohertz that comes with this unit to tune it in like I always do. And it happens to be that on my LSR, it reads 0.5 microhenries or millihenries or 500 microhenries, right? It happens to be on this unit 519 microhenries, again 0.5, with a Q of 1. So this is the value that I have for this unit when using the default generator that comes with the unit as built in when we're measuring a coil like this or any other coil on the unit. This might be a bit futile, but what I'm trying to do is see if I can use an external generator, which I'm doing now. I have it set for external generator, as you see right here. It's the only thing that I've set up differently. You see, I can even turn the generator knob right here, nothing happens. The external generator is set to my field tech, and it's somewhat limited. And the response at this frequency, which I've set for 25 kilohertz as opposed to 1 kilohertz, is 20 volts, which seems to be it's fully driven, which is the amount of voltage I need to get this needle to halfway. So if I set it for 26 volts, the needle will be a little bit that way, 27 a little bit that way. So 25 kilohertz is the maximum frequency I could get out of this field tech at the maximum voltage for this unit. So 25 is all I got without going to another device. What I want to know is if I get the same values, and this might be futile, especially for Q, because I'm so far away from the resonant frequency of this coil, given what it's designed for with the capacitor. And granted, the capacitor is obviously not involved with this, but what the coil is designed to do, that I don't imagine there might be a significant change from 10 kilohertz to 25. But we're going to find out. We'll take a look. I spent quite a while trying to dial this one in. Eventually I realized that because I'm already using the maximum voltage that the signal generator can provide, I don't have that ability to turn up the generator level to increase the sensitivity. One of the things that I did first was switch it to 1 millihenry, and that allowed me to use 0 and give me a little bit more sweep on this knob for sensitivity. But then I realized that I could use external detector and use my oscilloscope, and that's what I did. So instead of using this gauge right here, I shut this one off and used my oscilloscope, and that gave me extremely accurate results. But what I found was very impressive. First of all, it should come as no surprise that the inductance did not change based on frequency. We already knew that was going to happen. It turned out to be very much on par, and that shows me the screen worked very nicely. What I found was that at 25 kilohertz, the Q went from 1 to 450. And that tells me that at least Q is functioning with regard to not staying at one position. And Q is a function of frequency, at least with regard to this particular coil. Because as the frequency changed, the Q reacted in this coil. Also tells me this is an extremely high Q coil. It's a nice coil. What I'm going to do is I'm going to have to compare this impedance bridge against another impedance bridge to see what the Q of this coil is as compared to another known good impedance bridge. I'll save that for a different video. But I think in hooking this up to the external generator, I think I finally covered the last of all functions for this impedance bridge. By switching over to the 0 to 1000, I think I've covered the last possible function on this side of the impedance bridge as well. So I think I've covered just about every possible function that can be covered on the impedance bridge. I think this closes out this project with regard to the restoration and testing of this unit. Thanks for everybody who watched. participated online, made comments, and helped out. I hope you all enjoyed this video. I plan on making other videos in the future with regard to the restoration of Heathkits, and probably and most likely will be incorporating this impedance bridge in those videos for the purposes of testing.